Okay, and let's welcome to the stage Michael Palumbo from Flatiron. We'll be talking about granulation line distortions.
Yeah, hi, I'm Michael. I'm a postdoc at the Flatiron Institute. I'll be telling you why granulation is kind of scary. So granulation refers to the pattern of convective cells that manifest themselves on the surfaces of cool sun-like stars. So here we're looking at actually a movie of the sun's surface evolving over about 20 minutes. And we can see that these granules are constantly changing, emerging, disappearing. And the relevant time to scale here for the emergence, disappearance, life of a granule is about 5 minutes. And so long before we thought about radial velocity noise and finding exoplanets, we knew that granulation manifested itself in stellar spectra in a few key ways. As we heard from Jack, we know that granulation results in a broadening of your spectral lines more than you would expect from simple 1D radiative transfer. This is your macroturbulence. Granulation, as I'll talk a lot more about throughout the rest of this talk, also creates an asymmetry in your lines, a skewness or kurtosis, you could think of it in your absorption lines. And then it also introduces a net convective blue shift, and this is because most of that plasma is emerging out from the star. Most of the photons are from the granules, which are bright, moving towards you, blue shifting lines. And you see a characteristic trend with the depth of the line and the amount of blue shift you see. If you want to learn more about this, Momo Elvert is an expert. She has a poster, so go check that out. I don't know the number, sorry. But more on this asymmetry. So this asymmetry is essentially created by the fact that there's a strong contrast in intensity and velocity between your granule and your intergranular lane. You have more photons from your granule, which is moving towards you, compared to your intergranular lane, which is sinking deep into the star. And since we don't actually resolve these individual components when we look at a star, we just get a blended line profile that is skewed by these contrasting velocity and intensity components. And critically, this is time variable. And so if you were to look at an absorption line at the sun and look at its bisector, its asymmetry, evolving over time, you would see something like this. And this is actually data from the sun recorded at disk center. And so here we're looking at an iron line evolving over about, again, 20 minutes of time. Each frame here is 15 seconds. And we can see the line is changing its position, both in terms of absolute velocity and the skewness, the shape of that C shape is changing. You can see the curvature change in the upper and lower part of that bisector. And that is because, again, we have a constantly changing ratio of granule and lane. It gets more fun. If you were to look at a different line, you might see a different bisector. This is a somewhat provocatively chosen line because this line is actually a close blend of two lines, and so that's why we see a very different shape here. There's a line blend in the blue wing, which is dragging that bisector over. And in the sun, where we can actually resolve the surface of the star without interferometry, if you were to look at a different limb angle, you're probing different slant depths in the solar atmosphere. You're probing different velocity fields. You're seeing different ratios of granule and lane. You see a different bisector. And this all creates a source of radial velocity noise at the level of tens of centimeters per second. As we'll hear from Bill Chaplin shortly, one thing we do with p-modes, for example, is we can just bin over the noise from p-modes by exposing for some integer multiple of the period of the principal p-mode. And even though p-modes can manifest at the meter per second or exceeding the meter per second level, because of the characteristic of that physical process, if you were to integrate for long enough, you can bin down the residual amplitude from your p-mode to the 10 centimeter per second level or less if you do this properly. For granulation, unfortunately, simulations have suggested that because of the noise properties of this physical phenomena, if you were to observe your star all night even, you might not be able to bin down your residual velocity amplitude to the 13 centimeter per second level, where again, 10 centimeters per second is the RV amplitude of a semi-amplitude of an Earth twin orbiting a solar twin at 1 AU. So this is a problem if we want to discover Earth twins. We need to be devising granulation strategies that don't rely on brute force binning. And so one way to develop this is to look at the sun and to study granulation in the sun and devise methods where we know the ground truth radial velocity of the sun and devise methods that can cope with deviations in its apparent velocity. Unfortunately, we don't have ultra high spectral resolution, densely sampled time series of disk integrated sunlight where we can see these lines dancing around for the entire sun. We only have them for small patches of the sun. And so to cope with this, I spent my last few series of papers writing a software that combines disk-resolved observations of the sun into synthetic disk-integrated observations of the sun. That is, observations of the sun as if it were another star, where you are not resolving its surface. And this is powered by, again, very high resolution, very densely sampled observations of solar spectra. So we have 22 solar lines, and for each of these solar lines at about 40 disk positions, we have at least a 20-minute time series with 15-second sampling where we can watch these lines dance around and change their asymmetry. As a brief methods, what we do is we tile a synthetic stellar disk. We consider things like limb darkening, the rotational velocity of the patch, et cetera, all the necessary physics ingredients. And we essentially just inject a bisector dance into the appropriate tile. We sum over our spatial elements of the grid, and then what we're left with is a line profile or line profiles that are varying as a function of time. And again, the only thing that's changing from time step to time step is the shape of the line, owing to changes in granulation. There's no other planet velocity in here or no other velocity anomaly introduced by global stellar activity from magnetic fields, star spots, et cetera. And so what we're left with is a disk-integrated line, synthetic disk-integrated line at very high spectral resolution, RF 700,000, that is dancing at 15-second intervals. And we can study the properties of this and see what we can do about it. And in my paper, I show that we accurately reproduce line shapes. This is just a validation of the model. If we look at a time average line profile on the sun from a work that Momo is on as well, we can see that our synthetic disk-integrated IRM1 line profile agrees with what we see. And if we look at the bisector and model out a line blend, again, our bisector matches what we expect to see in a time average line profile. In my more recent paper, we do this for 21 more lines, and so if you want to see all those nitty-gritty details, I will direct you to that paper. Moreover, if you want to play with these time series yourself, I can provide them to you, or if you want to synthesize your own, thanks to some GPU magic, you can synthesize your own RF 700,000 time series of spectra in a matter of seconds, so that's cool. Okay, all that's to say, what can we actually do about granulation noise? Well, if we go ahead and look at each of those 22 solar lines, generate a synthetic time series, and measure how much variability we see there's a pretty big spread in the variability here. So I've just ranked each of these lines we studied from most variable to least variable. And there's about a 30 centimeter per second swing here from the most variable to least variable line, which is to say that there's a big difference here. If you could identify quieter lines, you could get perhaps a measurable improvement in your RV stability. But the issue is that we can't necessarily predict which lines should be quiet quite easily. So here we're looking at a scatter plot with the formation temperature of a line. That is, we've tried to map where in the atmosphere of the star this line is coming from. And for the 22 lines here, we have no clean correlation. If we were to look at a much larger sample of lines, we might expect to see a trend where a certain part of the photosphere might be more stable against granulation. But for the lines here we don't see that. We can also use line asymmetry information. And so things like the bisector inverse slope or bisector curvature have been long used to diagnose global magnetic activity. That is the change in shape of a line you would have from a spot, like Rachel talked about earlier. It turns out we can also use these to diagnose granulation just at a much more precise level. So here we're looking at the variability of a bisector exaggerated 50 times, and we can measure something like a bisector curvature for this. And we can see that it's actually quite nicely correlated with the anomalous RV that we measure, which is to say that if you could resolve the bisectors of individual lines for other stars, measure a very precise change in its curvature, you could use that to pull out how much of that radial velocity you measure is actually anomalous, that is, not corresponding to the actual center of mass movement of the star. In reality, the optimal bisector diagnostic and where you have to measure in the bisector varies line by line. This is not surprising. We have different lines with different formation characteristics. And if you want the full nitty-gritty details of that, again, I will direct you to the paper. But the summary is here. In general, what we're looking at here is the the raw RV RMS variability as the circles, and the improvement we get as diamonds. And so we can see we can correct our RV noise floor down by, in the best case, multiple tens of centimeters per second. There is a catch, though, which is that for existing RV spectrographs, at their resolution and at the signal-to-noise we obtain, we generally can't actually resolve this variability for individual lines. So here, we are looking at a synthetic time series, again, of a line wiggling, but this time at a more realistic spectral resolution and a more realistic signal-to-noise. And that correlation between the bisector curvature and the anomalous RV completely falls apart. And so what we need to be doing is binning lines. And of course, if you turn to your velocity fields chapter of Gray's stellar photospheres textbook, you'll see this figure where he stacks line bisectors and say they agree with each other. In reality, this is far from universal. If we look at our family of line bisectors here, these lines are very different. We can't nicely telescope those line bisectors and bin them together on top of each other. So the question becomes, how do we identify lines that we can bin together? Of course, in RV work, we get precision by binning velocities from many, many, many lines. This is almost an application of the central limit theorem, right? Our precision on any individual line for the velocity is low, so we bin lots of them together, get a better estimate of the actual velocity. But since our bisectors are different here and we're adding incoherently, if we blindly add lots of lines together, then we get a mess. We see no correlation between that bisector curvature and the anomalous velocity. Indeed, recent work attempted this, where they looked at bisector curvature in a binned line CCF and looked at the anomalous velocity, and they got, again, just a scatter plot with no correlation. And so what we need to be doing is selectively binning lines. And I'm running low on time here, so you just have to believe me. But the essence is that if we have spectra at high SNR and we bin together lots of lines which we believe behave similarly, then we should be able to actually resolve these changes in line shape from convection and use them to pull out deviations in velocity. So I'll leave it at that, put up my summary slide, and take questions. Thanks.
Excellent talk. Here in the front.
Hi, Elizabeth Newton, Dartmouth College. I was wondering whether there is room for more like a model that ties together different lines, like based on solar physics structure, like the atmospheric structure of the sun.
Yeah, there's room for that, and I think one of the things I'm trying to do right now is to map the coordinates in those bisectors, basically the depth or intensity in the bisector, to a temperature coordinate or an optical depth coordinate or a physical depth coordinate in the star, using just some simple 1D radiative transfer models. And I think we've heard this refrain a couple times. 1D radiative transfer models aren't accurate, but there's maybe some magic sauce in using an incorrect model that gives the right answer. So it could provide some insight into finding, okay, these parts of these lines are forming at similar heights in the stellar atmosphere. Let's just try binning those and see if we can get a coherent signal out.
Can you handle, Jeff Valenti, can you handle line blends at all? Because at some point, all lines are blended, right?
Yeah, that's also a scary thing to think about. I think we will have to be rejecting lots of line blends in order to do this well. And I think starting with the sun, we'll have enough signal to noise to do this, even being very rigorously rejecting line blends. But when we go to other stars where the signal to noise is naturally lower, we might have some problems finding enough lines that are decently unblended enough. Yeah.
I have faith that you can actually take care of blended lines, so I challenge you to do that.
Okay.
So you showed us the example when you had the really high resolution, what was it, 700,000 or something?
Yep.
And then you showed us the example of R of 90,000. What resolution in between there would you actually need to be able to sort of start to resolve these correlations in a meaningful way that they would actually contribute to mitigation strategies?
Yeah, so if you have, you know, at very high signal to noise, you can probably do this around the resolution of as low as 100,000 if you're binning together enough lines. But the problem is actually more in signal to noise. The bisectors are very sensitive to like an error and flux measurement. So I would believe this is possible with extant EPRV spectrographs, probably better around like the NUID resolution than around at KPF. Definitely doable, probably at Espresso UHR, you would have the easiest time with that.
Okay, we should move on, stay on time. Let's thank Michael again for an excellent talk.